Welcome to lecture 9 of module 7. In this lecture, we're going to show you how we get the wave functions of hydrogen. If you recall from the classwork that we did on the isotropic harmonic oscillator, I essentially told you what the answer was by telling you what these strings of B operators were and how they converted into Laguerre polynomial operators. Here we're going to actually go through all of those steps. That means this lecture is going to be a bit long, and also it is going to be quite technical. You may want to take a break from it from time to time and then come back to it. You may want to slowly take notes and see if you can follow along from one step to another. In any case, this is a difficult lecture that we're going to have today. Okay? Let's go ahead and get started. So we have this string of B operators that is acting on the auxiliary Hamiltonian ground state, and we want to try to evaluate what those operators are in a more simple form. And the idea is let's use the subsidiary condition, which relates the operator of radial momentum acting on the state to a polynomial in 1 over r acting on that state. This then gets rid of the momentum operators and replaces them by position operators. If I'm trying to get the wave function in position space, this is a good thing to do because I know what to do when a position operator acts on a position eigenstate, but I don't know what happens when a momentum operator acts on a position eigenstate. So this strategy of using the subsidiary condition is going to allow us to get rid of the momentum terms in the string. Unfortunately, because we have operators and they don't commute, the procedure is not completely trivial. It's actually a bit technical. However, the first step is actually fairly simple. So if we construct B dagger of r of n minus 2 and act it on the state n comma n minus 1, it's just 1 over square root of 2m pr plus ih bar 1 over n minus 1a0 minus n minus 1 over r hat. The plus ih bar is there because the B operator has a minus ih bar, and we are, of course, taking the Hermitian conjugate for the B dagger. Now, I can just substitute in what that PR is. I can replace that by the ih bar 1 over na0 minus n over r hat, and I factored the ih bar out. And now you can see that if I look at the terms that have the 1 over r, those guys just add together, I'll get 2n minus 1. If I look at the terms with 1 over a0, I can combine those over the same denominator, and I will get a 2n minus 1 over n times n minus 1. So we get this nice simplification. We can actually pull that factor of 2n minus 1 out if we would like. And you see we now have this polynomial in 1 over r. All right, that worked nicely. Let's take a look at the next string. If I look at the next string, I will have a B dagger r of n minus 3 times a B dagger r of n minus 2 acting on n comma n minus 1. We just substitute in what the B dagger r did on the n comma n minus 1, and then we still have this PR plus ih bar 1 over n minus 2 a0 minus n minus 2 over r hat acting on that polynomial. Now, of course, the terms that involve the position operators, they're easy to evaluate. With the momentum, we would like to put that momentum next to the state because then I can use the subsidiary condition on the top to get rid of it, but I have to commute it through that 1 over r term. So what we're going to do is we're going to replace the PR by that value, and then we're going to add in that commutator that we need to have. So when I do the replacement, I get this 1 over na0 minus n over r hat, same as we did in the previous calculation we did, but now I also have this extra term, which is the commutator of the PR with minus 1 over r hat. Okay, we can combine those terms just like we did before. The terms with 1 over r hat, they easily add. The terms with 1 over a0, I have to put them both over the same common denominator. I will get a 2n minus 2 over n times n minus 2a0, and I will get a 2n minus 2 over r hat. So we go ahead and make that simplification. Now I have a quadratic polynomial that I'm going to have to multiply out. And when we evaluate that commutator of PR with 1 over r, with minus 1 over r, is going to give me a minus ih bar 1 over r hat squared. I took the ih bar out of both the commutator term and the polynomial terms in the front. Now we simply have to do a FOIL and add all of our terms together. it's a little messy, okay? This is not a trivial thing to do. It's a little messy to get the FOIL to fully work out correctly. But, this is just a bit of algebra. I'm going to show you what it is. I do recommend that you carefully work this out for yourself, maybe even pause the video and work it out right now. So this is what we get when we've done that. And you can see now this is a polynomial in a 1 over r hat squared. I'm going to summarize these two results, and I'm also going to add in a calculation that I did myself for the next term. I do recommend you give it a try. It's not so hard to do, but you got to be patient to get through it. It might take you 10 minutes to get through the algebra to finish that. But it's a good exercise in terms of operators, and hopefully I didn't make a mistake and the answer that I wrote down here is correct, so you can check yourself. I do find when I do these calculations, it's very, very easy to make mistakes, and I often find I do make mistakes when I'm doing this. You might also notice that we factored out powers of 1 over r squared, and 1 over r cubed to make the polynomials normal polynomials in r hat. All right, so now what we're going to do, we've seen a taste of how this works, just kind of going term by term, and we also saw this is not something we really want to do for evaluating too many terms one after another. It gets very complicated. Instead, what we'd like to do is something that is much more general. We would like to explicitly work out an inductive proof to figure out what the polynomials are for the general case. So to do that, we need to have a base case. The base case is that first case that we worked out. And this is written out in the form that I had just mentioned, where we pulled out a factor of 1 over r hat as well, so that we have a normal polynomial in r hat over a0. We're going to do a little bit of rearranging of this, and I have just multiplied by 1, nothing else, or moved factors from one term to another. So in the first two factors, I just multiplied by a 2 over n in the first factor and an n over 2 in the second factor. In the first term in the polynomial expression, the one that's proportional to r hat, I took the n from the denominator and moved it into the term that is the expansion term for the parameter, and then I multiplied and divided by 2. So that's just an exact identity as well. And I'm going to get rid of the red. And now that we have done that, we're going to now look at the general induction case. For the general induction case, I want to write out what that string of b's are for some arbitrary case. I'm taking the case where the last b dagger operator is b dagger L. And we're going to write this in terms of some polynomial. So what we're going to say is that that constant term that we had out in front, that's going to get multiplied. I'm going to get one of those for every b dagger that I apply. So that's going to have a n minus L minus 1 to it. The operator term with the 1 over r hat as a prefactor, I'm going to get one of those as well. So that will have a n minus L minus 1. And then I'm going to have a polynomial that's going to go from a constant term all the way up to a term that is r hat to the power n minus L minus 1. You can figure that out just by counting how many b dagger terms you have. And then I lump all of the constants in the bj of L. This is still a completely exact statement because the only things that I'm really manipulating are the constants out in front, and those all essentially just go into defining what this bj of L is. Okay, so this is a perfectly general statement. Now for the induction proof, and of course our base case is given by b0 of n minus 2 is minus 2n plus 1, and b1 of n minus 2 is 2n minus 1 divided by 2 times n minus 1. All right, now what we're going to do for the induction proof, you might think about, well, what would I do? The simplest thing is to pull that factor b dagger r of L out to the left and have it act on the polynomial that is the L plus first polynomial. And that's indeed what we're going to do. We're going to pull one factor out for the induction step. We have to be careful to remember that the polynomial, the L plus first polynomial, involves both the 1 over r hat terms and the polynomial term in r hat. We have to make sure that all of those operators are to the right of the b dagger r of L when we're doing this induction step, which is why that exponent is not 2r hat over n a0 raised to the j power, but it's 2r hat over n a0 raised to the minus n plus l plus j plus 2 power, because that incorporates all of the r hat powers that appear to the right of the b dagger r of L term. Okay, now we have to plug in what is that b dagger r of L. We know exactly what it is. It's a 1 over square root of 2m. It has a PR term, has plus I h bar 1 over L plus 1 a0 minus L plus 1 over r hat. That's acting on everything to the right. I can just replace the PR using the subsidiary condition just like we used before, and then I have to add the commutator of the PR with that r hat to the minus n plus L plus j plus 2 term. We know how to calculate that. The commutator of PR with a power is just going to give me the exponent of the power and reduce the power by 1. To reduce the power by 1, that's the same as multiplying by a 1 over r hat, except for the case where it's r hat to the 0 power. But when I multiply by the exponent with the r hat of 0, that's multiplying by 0. So I don't really have to worry about that term. So I can actually just use that dividing by 1 over r hat to take care of all of those terms. And indeed, that is what I'm going to do. So when we put that together, the term in red, that's the term that came from the commutator. The other terms are the terms that came from the substitution of PR using the subsidiary condition, where PR acting on the state n minus 1 was equal to 1 over n a0 minus 1 over minus n over r hat, the whole thing multiplied by I h bar. Now we pulled the I h bar out, and then we're left with this contribution. Notice that we have two terms. We have a constant term and we have a 1 over r term. We're going to simplify the terms, get rid of the terms in red that cancel. You can see the n and the minus n will cancel out. I'm going to be left with this j plus 2l plus 3. Okay, so what you can see here is I would like to actually pull out the r hat factors to get it into the standard form. So we should have a 2i bar over square root of 2m na0 raised to the power n minus l minus 2 and an na0 over 2 r hat to the n minus l minus 2. So I'm going to take those terms out from this polynomial. And then what I'm going to do is I have an IH bar over square root of 2m. I'm going to pull out another factor of 1 over r. And I'm going to take that IH bar over square root of 2m. I'm going to divide that by an na0 and multiply the 1 over r hat by an na0. And then I'm going to do the same thing with a factor of 2. I'm going to multiply the constant and divide the power of 1 over r hat. And what you can see we get there is then this green and red term that we factored out. You can see there I have that na0 cancels and the 2 cancels, and it just corresponds to that original IH bar over square root of 2m and the 1 over r hat. But now you can see I can combine the red terms together and raise that power by 1, and I can combine the green and raise that power to 1. Now I have it in the standard form for the Lth polynomial. And when we look at the terms that are left after we've done that, you can see that we have terms that go like a power of r hat to the j plus 1 and of r hat to the j. The r hat to the j terms I'm going to leave the same, although I'm going to extend the sum to n minus l minus 1. And we're going to do that by saying that b n minus l minus 1 of l plus 1, that coefficient is equal to 0. And for the term with a j plus 1, I'm going to let j go to j plus 1, which means, or I'm going to let j go to j minus 1, which means that sum will go from 1 to n minus l minus 1. And then that b index is going to become a b of j plus 1. And the exponent will lose a term in the exponent when I do that. So I now have a combination of the b's. I have these terms with a bj minus 1 and the terms with a bj. And of course, we just set this equal to the expression above. You see now the summation still goes from j equals 0 to n minus l minus 1. The prefactors are exactly the same, and it's all acting on the same state. So we just have to equate that big thing in parenthesis with the bjl. So let me summarize what that is going to give you. When we do that, here I'm showing you that these polynomials are the same, but I really just care about the coefficients of the polynomials, so I can write it in this form. And I'm just reminding you of this fact that we use this condition that we defined b l plus 1 of minus 1 and b l plus 1 of n minus l minus 1 to be 0, because we need that in order for those terms to be defined in the summation. And we've now derived a recurrence relation between the coefficients of the different polynomials. Now, you might be saying to yourself, well, kind of, so what? This is still a complicated mess, and it is. And it's not like I want to actually try to solve that recurrence relation. Indeed, I don't want to try to solve that. But we knew in the last time when we were looking at this that the Laguerre polynomials have a very special property. And that special property was that they really look simple when we compare the ratios of consecutive terms in a given polynomial. So what I want to do is I want to calculate the ratio of the bj plus 1l divided by bjl, and I want to express it in two ways, in terms of the things on the left-hand side and in terms of things on the right-hand side. And so we go ahead and do that. We get something that's kind of big and complicated, but it just requires letting j go to j plus 1 for the numerator, and then just using the term with j for the denominator. But remember, the thing that's important about these Laguerre polynomials is the ratio of consecutive bj coefficients. So I'm going to divide the numerator and denominator by bj of l plus 1. Then I'll get the ratio of bj plus 1 divided by bj. And if you look on the denominator, I'll get bj minus 1 over bj. I'm going to just write that as bj over bj minus 1 raised to the minus 1 power. Okay, so I'm going to plug that in. This is exactly what I said that I did. I just divided numerator and denominator by the same factor. And now we need our induction step. So it may look like this induction step is coming out of the blue. And to some extent, it is using 20/20 hindsight from the fact that this problem has been solved other ways. But I do believe that if you continued on working through and calculated a number of those polynomials for the general case, for those low order polynomials, when L is very close to n minus 2, you would land on this result that bj plus 1 of L plus 1 divided by bj is given by j minus n plus L plus 2 divided by j plus 1 times j plus 2L plus 4. And if I let L go to L minus 1, you see I get the term in black. Our goal is to substitute the red into the right-hand side of the equation above and verify that we get this black equation. Sounds simple enough, but when you plug in, it's really quite a mess. Okay, this is what you get by simply doing that straight plug-in. I'll show it to you again. I just plugged in the two places for what those expressions are. In one case, I have to let a j go to j minus 1 in order to do the plug-in, and I have to remember that that term in the denominator is raised to the minus 1 power, but is just plugging in. Our next step is to put everything under the same common denominator. I recommend that you just look at the video right now. You may want to come back and try to do this on your own. The algebra is really quite painful. You might want to use something like Mathematica or Wolfram Alpha to help you with the algebra. But here's what it is. It's kind of a mess, but this is just putting everything over the same common denominator. And now we just have to evaluate this. And this requires you to just be very careful about how you expand these quadratics and to think carefully about how you can factorize them. It turns out both the quadratics in these square brackets, after you expand them out, they factorize, and you can get them in terms of two different factors, and then you get a cancellation of factors. And lo and behold, what you find when all the dust settles is you get exactly the ratio that you need for a Laguerre polynomial. So what we have established by doing this is that this string of operators gets written in terms of a Laguerre polynomial. We've only established that it's proportional to a Laguerre polynomial. We don't know the constant of proportionality yet. We're going to figure that out in just a moment. So I just want to refresh your memory what these Laguerre polynomials are. If alpha is not an integer, that generalized binomial coefficient m plus alpha over m minus j, that was written down for you in one of the pages during the class exercises when we were talking about Laguerre polynomials. We did it, I think, 2 lectures ago when we were doing the isotropic simple harmonic oscillator. I'm going to write them in a generalized form as aj superscript alpha comma m, just to keep everything straight. We can look at the ratio of those two terms. They become j minus m over j plus 1, alpha plus j plus 1. you can very easily read off of that what m and alpha are. So the string of B operators acting on the L equals n minus 1 ground state is proportional to a Laguerre polynomial with m equals n minus L minus 1 and alpha equals 2L plus 1. And the argument of the Laguerre polynomial is 2r hat over NA0. All right, that's summarized for you here. As I told you, there's a prefactor in front, this DNL, that we have to figure out how to calculate. You might want to think a little bit about, well, how would I do that? Okay. Take a few seconds and think about it, and then I'll reveal to you how I did it. You might be saying to yourself, I have no idea how in the world I would do this. This algebra looks so complicated. How can I go forward? But really, I want you to concentrate on our French cooking attitude. There was nothing in any of this derivation that was particularly hard. We used a couple of commutators and we just did some algebra. Okay, you had to do a reasonable amount of factoring if you want to work through all of the steps. But if you trust me, the algebra is really not that complicated. Okay, so when we think about what happens when the B operators act, the thing gets complicated when this radial momentum operator has to have a commutator with a 1 over r hat term. And that's when things get complicated. Because we have terms that go like constants plus powers of 1 over r, if I look at all of the constant terms in that string, so the terms that have that are constants, the highest order term in the polynomial, the one that's the constant term, because remember, I'm factoring out this factor of 1 over r hat to the n. So that constant term becomes the r hat to the highest power, which is n minus L minus 1 in this polynomial. That term actually never involves any commutator with a p hat r, because when the p hat r acts is a commutator with a 1 over r hat, it always gives a higher power of 1 over r hat. So that means we can just directly calculate the constant term, or the highest order term in the polynomial, just by looking at the constant terms in the b hat daggers. Okay, so that is what is done for you on the right-hand side. You see every b hat dagger has a term that's multiplying the constant of an I h bar over square root of 2m. So we have that raised to the n minus L minus 1 power. And then what we're going to have, because we have to do the substitution of the PR acting on the state n comma n minus 1, we just don't worry about the commutator. That means that the constant term will get a 1 over NA0 from the PR term, and it has a 1 over KA0 from the B dagger term, and that K is going to run from L plus 1 up to N minus 1, because as you remember, the term in that denominator is an L plus 1. And now to get the term on the right-hand side, I have to go in and look at the Laguerre polynomial formula when J is equal to M. When J is equal to M, that generalized binomial coefficient becomes 0. And what I'm left with is minus 1 to that, to the highest power. I said M. What I meant is, in this case, since M is n minus L minus 1, I mean, and when J is equal to n minus L minus 1, I'll get the remaining prefactor, which was a minus 1 to the M over M factorial, which becomes minus 1 to the n minus L minus 1 over n minus L minus 1 factorial. And then we just have to remember that this term has these other constants in front, the DNL and this 2IH bar over square root of 2M NA0 raised to the n minus L minus 1 power. Now these guys are equal. So we just have to calculate what they are, and that will determine what DNL is. This is just algebra here, okay? I'm going to take you through it step by step, show you how you do it. Okay, now all that I did here was cancel the common factors. You can see there's an IH bar over square root of 2m on both sides. They're raised to the same power, so I can cancel those on both sides. I'm left with the 2 over NA0 to the n minus L minus 1, and everything else stays the same. Now, we're going to look at this infinite product. What I want to do is I'm going to factor out a 1 over NA0 from each of those terms. That's going to give me a 1 over NA0 to the n minus L minus 1. And I get an n plus k over k, and that's a product. You can see that's going to be related to factorials. I can again cancel the 1 over na0 on both sides. I'm going to just be left with the 2 raised to that power. And let's talk carefully about the factorials. So let's look at the numerator first. We have the n plus k. I start that off at n plus l plus 1, and it goes all the way out to 2n minus 1. So it looks like a factorial. It looks like 2n minus 1 factorial, but someone divided out the terms starting from n plus l, and so I have to divide that by n plus l factorial to get that. And then similarly on the denominator, I have something that's going to look like n minus 1 factorial in the denominator, but I have to multiply the numerator by l factorial because those lower terms, the ones from 1 to l, are not in that product. So what we get is then this 2n minus 1 factorial, l factorial, divided by n plus l factorial, n minus 1 factorial. Now I can just move those extra constants from the left-hand side to the right-hand side, and I get what dnl is. So dnl is equal to this mess. I'm not going to read it out for you. It's simply just doing that quick step of algebra. But now we can plug that into our expression above and get what this string of b daggers are when they act on the state n comma n minus 1. All right, and this is what it gives. Again, not going to read it out for you. It's kind of complicated, but this is just a substitution in. There's nothing particularly fancy or complicated or subtle about what I'm doing. All right. Now, what I'm doing here in going from the next step is I'm going to do some simplifications. You see there's a 2 to the n minus l minus 1 in the denominator and in the numerator. That can be canceled. You see that there's a minus 1 to the n minus l minus 1. I can bring that into that other power. And so what we get is minus I h bar over square root of 2m na0. The factorial terms stay all the same. The power terms stay all the same. The Laguerre polynomial stays the same, and so does the state. Okay? Now, there's one other term that we need to multiply this by because we've been working without normalizing the state n comma n minus 1, or really the state with the string of the b operators. Now, we know how to do this with factorization. We worked this out a number of times before. We have this term that's 1 over square root of the difference of these energies. And so what we have to do is just plug in what those energies are. So there's also a factor that we're going to need to guarantee that the auxiliary Hamiltonian ground state is normalized. We'll get to that last. For now, we're going to work on this product of the energy factors. And we have to plug in what the energies are to get En minus Ek is E squared over 2A0, 1 over K squared minus 1 over N squared. We put everything over the same common denominator. We get N squared minus K squared over K squared N squared. We recognize that N squared minus K squared can be factorized into N plus K times N minus K. So we go ahead and do that. And now we've got this product that is running between K equals L plus 1 all the way out to K equals N minus 1. So this is going to be very similar to what we looked at before. You see, I'm going to have a factor of n squared for each of those terms. I can just pull that out. The k terms, they're going to be a ratio of factorials, as will the n minus k and the n plus k. Now, you have to just sit down carefully and work this out. I do recommend, again, that maybe you pause the video, see if you can work out what those factorials are. Each one of those terms will yield a ratio of 2 factorials, one corresponding to the largest value of the term inside the parenthesis, or the term in the product that we're taking. The other one will involve a correction term to compensate for the fact that not all terms are in most of those factorials. So go ahead and do that, and you get these results. And we have to remember that there's an overall square root, so I'm taking into account that square root as well. And I'm putting things into the numerator that were in the denominator and so forth. And we get this result. We get square root of 2a0n divided by e times n minus l minus raised to the n minus l minus 1 power. We get n minus 1 factorial square root of n plus l factorial divided by l factorial square root of n minus l minus 1 factorial times 2n minus 1 factorial. Okay, kind of a mess. I have to bring that in with all that other stuff that we had before to normalize that state of that string of b operators acting on the state. So I go ahead and do that. There are some cancellations that occur, and I've done that for you. We have this minus I to the n minus l minus 1. We have this n minus l minus 1 factorial, 2n minus 1 factorial over n plus l factorial, all square root. We have this power of na0 over 2r hat to the n minus l minus 1, the Laguerre polynomial, and the state that it's acting on. All right, now let's work on the wave function. To get the wave function, I have to multiply by the position bra. I'm going to multiply by a position bra that is expressed in the spherical coordinates. So I'm going to have a theta phi bra, and I'm going to have an r bra. They're written as a tensor product. The r bra goes with the NL state, and the theta phi goes with the LM state. Remember the overlap of theta phi with LM, that's the spherical harmonic, y LM of theta phi, so that's easy to work with. The r overlap with the NL, that's the radial wave function that we're trying to calculate. So let's go ahead and do that. We can express it in the more standard form, psi NL of r and y LM of theta phi. Let's focus on the psi NL of r. When I operate the bra on this operator, because it's a bra of r hat acting on that state just gives r. So I can pull the power of r out, replacing the r hat with an r, and I can pull that Laguerre polynomial out, replacing the r hat with an r. And of course, the numbers get pulled out as well. So I'm left with the auxiliary Hamiltonian ground state. That's the bra of r with n comma n minus 1. And then I'm left with these other factors in front. All right, so we have to calculate this auxiliary Hamiltonian ground state. We're going to go back to that exercise that might have seemed a little bit cryptic that we did on page 32 of module 7, where we showed that when we have this subsidiary condition, which turns out to be BR of n minus 1 acting on n comma n minus 1 equals 0, when that occurs, then this operator p hat r plus I h bar over r hat acting on the state 1 over r hat to the n minus 1 n comma n minus 1 is equal to I h bar over na0 1 over r hat to the n minus 1 n comma n minus 1. That's an eigenvalue eigenvector relationship. The eigenvalue is pure imaginary. That's because the operator is not Hermitian. All right, we're going to be using that along with the results that we had for the radial translation operator. So again, you have to go back to module 7, lecture 6. It wasn't that long ago where we worked out what the state r was in terms of the state r at the origin and the radial translation operator e to the I over h bar r number times p hat r plus I h bar over r hat operator acting on the state n comma n minus 1. We do what we typically do, and there's nothing else we can do with an exponential. We expand it in a power series. So we're going to write that as the sum j equals 0 to infinity, I r over h bar raised to the jth power, 1 over j factorial, bra 0 r, bra at the origin of r, times this operator p hat r plus I h bar over r hat to the jth power. We want that to act on the state 1 over r hat to the n minus 1, n comma n minus 1. So I'm going to multiply by 1 before I work out that expansion. And then I can take that r hat to the n minus 1, acted on the state, it becomes r to the n minus 1 and pull it out. So that's what I do. And now I'm going to expand that r bra in terms of the radial translation operator. And I pull the factors out. I only have to keep the operators inside that bracket sandwich. Now what you see is that operator, p hat r plus I h bar over r hat acting on that state. It's an eigenstate. So I can replace that by its eigenvalue, which was I h bar over na0. So I go ahead and replace that by I h bar over na0, and I can pull it out because that's a number. Now you see that the i's are going to multiply together, give me minus 1. The h bars will cancel, so I'll get minus r over na0. And of course, look at that summation. That's just the exponential. So I can rewrite that as the exponential. And now I find people get really confused. They look at this and they say, oh, something's wrong. That's infinity. Okay? Now I want to argue that that is not infinity. Indeed, if you look to the left-hand side, you see that this expression r comma n minus 1, which I could evaluate at r equals 0. Look at the left-hand side, okay? That behaves like a power of r to the n minus 1 as r goes to 0, because that object in red is just a number. If that bracket on the left-hand side behaves like r to the n minus 1 as r goes to 0, if I divide it by r to the n minus 1 and then take the limit as r goes to 0, I will get a number. So indeed, bra 0 sub r, 1 over r hat to the n minus 1, n comma n minus 1, that actually is a number. Okay? If you're having trouble with that, send me a note or we'll talk about it in class, but think about it, take a look, rewind about 30 seconds, see what I said about it, see if that sinks in. But that object is a number. It is not infinity. Okay? And that is our normalization constant. So we're going to determine that like we determine any normalization constant. We have to calculate the integral. Now, the integral of the angular parts is normalized because we have the YLMs, so we don't have to worry about that, but we do have to bring in the r squared that comes from those angular terms in the measure. And so when we square this, we get an r to the 2n minus 2, but then we get two factors of r, so it becomes r to the 2n. The exponential, I have to double the exponent, e to the minus 2r over na0. And now I have to do that integral. So I'm going to do a u substitution, let 2r over na0 be u. I get a factor out in front, na0 over 2 to the 2n plus 1. I have an integral du, u to the 2n, e to the minus u. Now you can shove this into Wolfram alpha to get what the result is, or you can remember Feynman integration. I can put an alpha in that exponent, recognize that this is a 2n-fold derivative of that with a minus 1 to the 2n. And then if I evaluate that and then set the alpha equal to 1, you find that that's going to equal 2n factorial. So that integral becomes 2n factorial. And this object multiplied by the square of the normalization constant must equal 1. And so we immediately get that this normalization constant is 1 over the square root of that term. So I take 1 over the square root of this term. So you see I get a 2 over na0 to the n plus a half, and I get a 1 over square root of 2n factorial. So that's the last thing that I need to multiply. We need to multiply our expression by r to the n minus 1, e to the minus r over na0, and then this constant 2 over na0, n plus a half, 1 over the square root of 2n factorial, and that will give us the wave function. All right? So there it is. That is our full wave function. Of course, it's a little bit inconvenient to have this factor of minus I to the n minus L minus 1. As you remember, eigenfunctions are defined only up to an arbitrary phase. So we can actually remove that, which we do. And we're also going to simplify these terms, get them all into an appropriate order, which is also what we have done when we have done the simplification. And there you have it. That is the wave function. Now, I do want to caution you, if you try to compare this with what you'll see in about 90% of the quantum textbooks, the numbers out in front won't be the same. And that's because they use a different form of the Laguerre polynomial. The form that I'm using is less popular, but this is the form that actually is in Mathematica and Wolfram Alpha and all of the algebraic manipulation programs. So it's best that you actually learn with the one that is the one that you would work with if you want to work with an algebraic manipulation program. So that's why I've chosen the less popular formulation of the Laguerre polynomial, but I just want to caution you about that. This is also the form that you will find if you look up in Wikipedia for Laguerre polynomial. This is the form that they use there. All right, wow, this was a lot of work, but we did derive this wave function, and if you think about it, the only thing we used was the canonical commutation relation. Pretty impressive. As I told you, the skills that we're using and learning and that we're being able to apply with these operators is really powerful. We were able to calculate the full wave function of hydrogen simply by using the fact that the commutator of x with p is IH bar. It kind of blows my mind every time I see that. Okay, that is the end of lecture 9 of module 7.